All right, folks are still jumping on, but we will jump into the agenda. Can everyone hear me okay? When I'm facing the microphone at least?
Yes. Yeah, we can hear you fine, Sam.
All right, good, good.
Where's that?
Someone has a very, very cute kid in the background.
Sorry.
No worries at all. No worries at all. I love to have kids part of the meetup. Learn machine learning early. I am going to mute everyone out real quick, and then feel free to unmute yourself when you'd like to chime in. All right, so the usual agenda, I will run through a quick few words up front. We'll spend about 10 minutes kind of catching up on the month's activities, podcasts, etc. Then we've got our main presentation, which will be by Kelvin, and I'll introduce that later. And then hopefully close out on time. We've been pretty good about that so far. So a few quick words. We still need an August presenter. So if anyone is interested, hit me up either via Slack or email, or you can fill out this call for papers, which is at this link here, twimlai.com/meetupcfp, and hope you'll participate. If not in August, at a future time. You don't have to be an expert. You just have to be willing to dive into a paper and present it. I'm assuming everyone on the call is familiar with the Fast AI course that we're doing. I think we talked about it last week as well. We are working on the second week of lessons now, so it's not too late to jump in. The first week is actually pretty light, so not too late to jump in and catch up with us. If you'd like to do that, all you need to do is jump on Slack and subscribe to or join the Fast AI channel and just jump into the conversation. If you haven't been on Slack for a while, if you've been a part of the meetup for a while but haven't been on Slack, the conversation there has been quite lively since we started the Fast AI study group. So you'll want to check that out and get reacquainted and replugged in. So Nick is going to be presenting at our next meetup on quantum machine learning. And here's a link to the paper that he's presenting. And I think I've got, where did I put that? Link to the archive here. Should be an interesting one. Nick, thanks for stepping up to present. I'm really looking forward to that discussion. In the past, we've leaned pretty heavily on the Zoom Q&A for this session. But since there is a lot of activity in Slack, feel free to ask questions there on the Meetup channel. And Kelvin, just so you know, I'll be keeping an eye on the Q&A on the chat as well as the Slack. You don't have to try to do all that and present. I will interrupt you when folks have questions, or you can periodically ask for questions and I'll monitor them. All right, so now it is time to open it up for community discussion time. Some prompts here, but feel free to chime in on anything that's been on your mind since we last met. Question and comments on recent podcasts, thoughts on guests that you'd like to hear from, thoughts on what you're working on or what's caught your interest, any new papers or projects that you've seen or things that you're working on. Things that you've seen in the news. It's all open, and so feel free to unmute and jump right in. Who wants to go first?
Oh, hi there, it's David. Just a quick comment. There's been a lot of activity, very interesting activity around using machine learning in agriculture. There's a very interesting article I could post back to you around a group that's using it to reduce the amount of pesticides to very microscopic fraction of what's currently used, and it seems to be a very hot topic. I'd be curious to see if we could find one of the people working in that space and have them either do a TWiML talk or at least chime in and give us some thoughts on that. That would be very interesting.
Awesome. I will do that. In fact, I could flip through my stack of cards here on my desk. And I met at the Train AI conference, someone from Blue River. Blue River is the company that got acquired by John Deere not too long ago. Their first project was this thing called a lettuce bot. And basically what they did was they hooked this contraption, for lack of a better word, up to a tractor. And this device had basically cameras that pointed down, and they use CNNs and other things to kind of determine, kind of sort lettuce from weeds as they were going down the rows. And they would use, I think, like spot blasts of fertilizer and or pesticide to promote or kill off promote the growth that they want and kill off the weed, and also to kind of thin and regulate the rows. So I've got a contact there. I'll reach out to them and we'll see what we can make happen, David. Nick, did you unmute?
Yeah, I did. I have a blog post to share. I just published it a week ago. I just posted a link. It's basically a review of a recently published paper on the subject of information theory. So it's kind of a tangent to the themes of this, but it's definitely relevant to the discussion I'll be conducting at the next meetup. So it's information theory with relevance to classical and quantum information.
Okay.
It's a review of a paper that the physicist Edward Witten just published, who's fairly well known from the string theory world, and he's kind of apparently getting into the information theory realm. So
I read something recently, I don't know if it was your blog post or something else, that talked about how information theory was basically, you know, we don't talk about it in the context of ML, but it's basically fundamental to all of statistical machine learning, or at least, you know, that may be a bit broad, but it's fairly fundamental to a lot of the things that we're doing, or at least it informs kind of a lot of machine learning.
Mm-hmm. It's definitely relevant. Yeah, as far as the way to, you know, translate from a machine learning algorithm to information theory is a little over my head, but it's definitely applicable.
Awesome. I'll definitely take a look at that. Anyone else? Anyone take a look at this at Google's AI principles? I haven't read through these yet, but I saw some of the chatter on Twitter. I'm assuming this is at least in part a response to the hubbub that we talked about last time about duplex. Any thoughts on this?
I mean, they're the first, right? They're the first ones to come out with a public stance on these issues as far as a, you know, public company. So they're definitely acting as leaders in this aspect.
I haven't read this specific article, but I'm very, very interested in how machine learning affects the behavior of people. I was very interested in your latest TWiML talk, actually, talking to the gentleman from LinkedIn. One of the insights I gained from that paper, in addition to the very interesting thing about using graphical models as an insight to understanding probabilities, was essentially the fact that they're modifying the behavior of the people using LinkedIn. And I don't think there's been a lot of real serious research been done on the effects of tweaking machine learning algorithms on a social website and the impact that has on the behavior of the people who are actually interacting with that website. So that's a very keen topic of interest for me. I have a group of collaborators I work on in this area, and that's a very big concern, the fact that there's nothing to even regulate or even understand the impact that these various different systems have. So I think this is highly relevant and very timely.
Yeah, where I've seen conversation about that and maybe even research, although I can't point you to anything in particular, is around the whole concept of the filter bubble and Facebook, and how Facebook, you know, in the context of Cambridge Analytica and all that, how Facebook is, you know, changing the way political systems work and people behave and politics works and all that kind of thing. But I think the LinkedIn examples were a little bit more subtle, and they were kind of interesting in that regard.
Yeah, we had a meetup last night and we're discussing the duplex thing, and I saw you discussed it last meetup. But yeah, we thought that it was a little bit overblown, the sort of criticism. But then we're also discussing, there's another product called Lyrebird.ai that allows you to tune a voice to be your voice. And we're sort of saying, well, that element of now the voices could actually be sort of influential to help you to click through to an ad or something like that. And we just discussed this sort of thing about what sort of regulation will some of the big vendors self-regulate on the way these techniques are used. So I definitely want to read this article.
Mm-hmm. Yeah, if I remember correctly, the spelling of that is livebyrd.ai.
L-Y-R-E bird.
I knew it was weird. L-Y-R-E-B-I-R-D, regular B-I-R-D?
Yes, yeah.
And there's a very strong thread in the SIGGRAPH, in the ACM SIGGRAPH proceedings around much more sophisticated examples of this, which include video. So this whole AI impersonation space is very, very active in the research side. I do agree.
Yeah, it's certainly creepy, you know, bordering on scary, some of the stuff that is happening. And when you look at like the, you know, this kind of stuff, Lyrebird and the whole deep fakes thing, and then you look at some of the recent, I don't know if you've seen the NVIDIA research that use GANs to kind of generate celebrity faces that were like photorealistic. You could certainly, you can see how we're, you know, quickly approaching a time when media, you know, we can't trust media in the same way, right? It changes the game there. And it shall definitely be interesting. I had another, what else did I have here that was interesting? Anyone see this? I haven't had a chance to dig into this, but there are a couple of papers recently on interesting things happening in natural language processing. This paper, I think, grew out of this one, which was written by Jeremy Howard, who's the Fast AI founder, and Sebastian Reuter. OpenAI released a paper, published a paper on their blog, or published a blog post today talking about this. It's a use of unsupervised pre-training to improve NLP applications. I haven't read it. I've just seen kind of the tweets about it, and I was curious whether anyone's taken a look at this at all yet. Should be interesting. If it's not already on your radar and you're interested in NLP, it's worth a look for sure. All right, so I think it is time to introduce you, Kelvin, and kind of pass the baton over. So Kelvin Ross is going to, I forgot to change the picture again. Did I do this last time too? I've done this before. Sorry about, I didn't change the little meetup picture here. Actually, I stopped sharing, so it's only on my screen. But Kelvin, I am passing it over to you. You can unmute yourself and find the share screen button at the bottom of the Zoom window and dive into your presentation.
to the top of the presentation deck. Okay, how's that looking? Can you see the first slide?
Looks good for me.
Cool. So yeah, today I'm going to walk through the Cardiologist-Level Arrhythmia Detection with Convolutional Neural Networks paper put out by a team at Stanford. Yeah, so this sort of relates to an area that we work in here in healthcare. So I'm part of IntelliHQ. It's a non-for-profit alongside Gold Coast University Hospital, tertiary hospital, and we've set up an AI Innovation Centre working with our local universities and industry, looking at how we translate and innovate and commercialise to actually get AI within the clinical workflow. So probably a little less emphasis on research, but we're finding that we're building up research teams, training up some data scientists, and looking at even novel ways of that, like taking university undergrad students and putting them through things like the Fast AI program and Andrew Ng's course. And, you know, we're just finding the universities locally are a little bit slow at, you know, getting on board with some of those sort of latest approaches and things like that, but the MOOCs are really good at delivering. So to set the scene of this paper, I just want to talk a bit broadly first about what we see the vision of healthcare. And part of that's driven by the driverless car journey, where with the driverless car, we've got sensors, we've got LiDAR, we've got you know, cameras and GPS and map data and so on. And then we can start building up models to actually help the car make those decisions of what to do, you know, to turn left, turn right, accelerate, brake, and so on. And ultimately to plan out to get sort of safe delivery or safe arrival at the destination. So we see the precision medicine journey as more or less that same journey. So how would we sort of build this driverless car type concept, but in a medical context, where we can have a lot of censored data and a lot of information coming in that tells us about, you know, where we perceive the condition of the patient at the moment. We can then look at what actions and what interventions are going to be most appropriate to undertake with them. And really the goal is to get them through that journey so that they're discharged more healthily from hospital. So fundamentally, we've sort of started off in the intensive care space at the hospital. And the reason for that is it's a very data-rich environment. We're already IoT'd to some extent. People are wired up to monitors. We've got ECG data coming in, real-time streaming data on blood pressure and you know, ventilation and other physiological measurements. And in addition, we've got medical records that have our lab results and radiology results and all these other things coming in. So we're seeing that in that area, we're starting to develop some really interesting research about early prediction of conditions like sepsis and so on. And what we're seeing is almost this setup of, you know, a diagnostic workstation that physician or clinical people might sit in front of that actually helps diagnose and helps point those physicians in the right direction. So it's almost, we're seeing this driver assist model starting to work to help clinicians. But as we move, so in our hospital, we're a sort of a tertiary hospital. Our city has about 600,000 people. It's the main hospital here. So we have an ICU area with 25 beds that generates in our medical record system about 250 million rows of data. If we think about the data that we've just ran a sort of project with Amazon starting to collect all the streaming data from ICU as well. So all that 240 hertz ECG data and blood pressure data and so on. That generates about 5 megabytes of data per patient per day. But then if we think about moving from that space to then having monitors for all patients in the hospital, all inpatients and then outpatients, what you see is these numbers start to grow. And if we think about, you know, in ICU, we pretty much have one nurse to each patient sitting there watching the monitor and can sit there looking at alarms and working out what goes on. But as we sort of scale this 1,000 times, we can't then have enough staff to sit there in front of these, you know, data sets streaming in to try and work out what's going on. And this is where, you know, AI becomes essential to actually provide that monitoring and support for the deteriorating patient as they continue on their journey. So that sets the scene a little bit for, you know, this, you know, the relevance of this paper. So the paper sort of started off talking about, back in 1996, they said there's about 300 million ECGs recorded annually. And I would say that number's probably increased tenfold with the growth of wearable devices and other things like that since that time. So that's a lot of information that's flowing through. And one other point I just put in there, the website's a good starting point for the paper. So what's an ECG recording? So an ECG is monitoring the electrical signal that's passing through the heart to fire off the different chambers to pump the blood, right? So typically, you know, the sensor's recording the electrical signal as it passes across a cross-section of the heart, and then that indicates which chamber of the heart is firing at various times and how that effectively is pumping blood. And hopefully I've got a couple of our physicians on the line as well. So yeah, if I'm a data scientist and a systems engineer, so I've worked in the e-health space for a while, but if this is too simplistic, please, Brent, chip in at any time to explain the clinical side of it. So the clinical people typically would, you know, they're trained to analyze these waveforms. So they would sit there and visually inspect the graphs that are produced, and they're trained to actually look for variations in those signals to determine various sort of abnormalities in the way the heart's actually pumping the blood. So, you know, a common heart disease is atrial fibrillation, which, you know, that's a leading cause of stroke, as, you know, the way the vortexes get built up in the sort of atrial chamber allows blood clots to sort of sit there within the heart, and then finally they can be pumped up to the brain and cause stroke. So these conditions might exist for some time, well before, you know, a stroke might occur. It might be several years of this condition occurring until finally a stroke occurs. So hence, you know, important to sort of diagnose these conditions, and then it can be treated with different drugs and so on. The traditional methods of analysing these ECG signals are using sort of signal processing techniques. So each of these waves represent different elements of the heart firing off, and then we start looking at different measurements. So a big important one is this RR interval, about how far the waves are spread out. So signal processing, fast Fourier transforms, and these other techniques have actually tried to analyse these signals at different times and make these measurements. So pretty much this is sort of the techniques that are used and implemented in a bunch of ECG devices at the moment. Cubios is a popular tool set for analysing this data over long periods of time, and a lot of papers and publications have been built up using these methods of measurement to then determine certain heart conditions. But I guess like other areas like image recognition, speech recognition, audio, what we're starting to see is to the point where neural networks will start outperforming these other rules-based traditional systems. And, you know, why do we want to do this? I think I just mentioned that ECG and in, you know, heart rate variability over time is a predictor for many diseases: heart disease, onset of sepsis and infection, stroke risk. It's a good measure of stress. We can predict fatigue, and even things like concussion and so on. We can detect this from ECG signals and the way the heart adapts its signal. Okay, so this paper, they collected a lot of data from these wearable patches. So there's this Zio patch from iRhythm. So I think the study was in part supported by iRhythm. And so these patches, oftentimes when somebody might suspect there's a heart problem, they'll put a halter on and have a wearable ECG to collect some data over some time. That data then comes back to the hospital, and a technician or a cardiologist would then inspect the signal, looking for issues in that. This device says it can be worn up to 14 days. There's many other devices out there. Some, you know, in a hospital setting, they typically use an FDA-regulated device, but there's many other, you know, cheap non-FDA regulated devices for like $25 that you can buy from China. Whether you would trust those, you know, that's another question. Some are adhered to the skin, and there's definitely challenges around that, and others might be stitched into garments or worn in a halter and so on. So the core of the paper was they took these ECGs and looked at just taking 30-second slices of them. The ECGs recorded at 200 hertz from this device. So there's 200 measurements a second. Now, a lot of the research says you need at least 200 hertz signal to really do this heart rate variability analysis at a sort of a diagnostic level. Many of the newer devices now are even up to 1,000 hertz, you know, particularly if you've got neonatal, pediatric kids with fast heart rates. You often might need, you know, even faster signals than that. So they applied a sequence-to-sequence model. So they've got a sequence here, 30 seconds to 200 hertz. So what's that? 6,000 millivoltage measurements, looking at the heart signal. And then that's fed through convolutional neural net, or ResNet, which I'll talk about later. And it outputs a sequence of 31-second labels. So for each second, we're indicating what is the sort of waveform at that point. And then each label comes from 14 different classes. So a normal heart rate is this sinus one here. That's sinus. Then oftentimes we might just have noise in the signal. So that's where we say we don't have a good quality signal. We just want to take that out. Otherwise, we're looking at sort of diagnosing these other abnormalities like atrial fibrillation and so on. Okay. At the very end, in the appendix of the paper, you'll see some different classes and what some of those waveforms look like. So visually, you can see these are the kinds of things that visually a cardiologist or a cardiology technician would be looking at the waveform visually, maybe getting some measurement rulers out and trying to measure, or using Cubios to analyze these signals to try to spot these variations, okay? But you can see in some areas that, you know, the sinus rhythm being the normal one, you know, it often requires a trained eye to then separate that from, say, atrial fibrillation. In the appendix, it's also got the training set numbers and the test set numbers, which I'll come back to in a moment. Okay, so how did they approach this? I'll talk about the model in a moment, but the model's a fairly standard model. Really, the big advance in this paper was the amount of data and labeling that they collected. So they've taken very much a traditional supervised learning approach and more or less in brute force applied you know, a labeling approach and then a testing approach. And you'll probably find the approach that used a little bit different to other areas in the way that they've used different levels of qualification. So in setting up the training and validation set, they've got close to 30,000 patients. And that's created, from that, they've got 64,000 30-second ECG traces, right? So then each of those ECG traces, they've got to create the 30-second labels. And they've done that manually, almost in a big mechanical Turk style approach of taking certified cardiographic technicians. So again, there's a you know, a board certification approach for people being certified to do that. So it's not a cardiologist, this is a technician that's done that. And they've gone through and manually labeled every second one of those 14 labels. So they built a custom web annotation tool to help with that. And then they've sort of split that into 90% and 10% validation data split. And, you know, as another side note is there's no patient overlap between those data sets. So they've taken care to segment that. So that's a fairly massive piece of work. If you think about the time it would take an individual to label the 30 seconds, that's, you know, a fairly sizable piece of work to label 60,000 pieces of data. Okay, then, so the model is basically a one-dimensional residual network.
Hey, Kelvin, before you dive into the model, maybe this is a good time to see if anyone has questions about the medical part and some of the background. Any questions?
So there's a whole bunch of assumptions that have been made in order to even get to this point. You know, the idea is that 30,000 patients, there's sufficiently consistent information in their EEGs or ECGs that finding patterns amongst them is actually even useful or valid. I assume that that's just a given. Are there a list of assumptions like that in the paper where they basically make these broad assumptions that the technicians are, you know, operating at a certain level of error and that there is consistency in the data? I mean, clean data is the absolute kind of gold standard for machine learning activities. And to me, there seems to be a lot of areas in this particular experimental setup which might not have ideal. I understand that there's a lot of tradition and history here, and you really have to work within what the medical tradition knows and understands. But I find it a little bit concerning that there are all these implicit assumptions around these things that are essentially just givens. Any comment on that?
Yeah, no, you make a good point. There's really no discussion about, say, the sampling bias that they might have in that data set in terms of how they've selected or what they filtered out of the, they said they had something like 300,000 patients. So how did they choose the 30,000 out of that 300,000? So we've just published submitted a medical journal paper, and a big part is that consort diagram about how you've selected the data in the first place. Yeah, that's a really important point. I'll talk a little bit about the testing, which sort of uses a board of cardiologists, but yeah, there's not really any discussion about even that distribution of classes and how that might match the real world, or whether, there's been a bunch of studies where even ethnic diversity is a big issue, things like, mammograms and so on. So whether that's been covered off. It's, there's a lot of gaps around that sort of data selection side.
Yeah, looking at the table in the back of the paper, it looks like if I'm interpreting this correctly, for some of these conditions, like we're talking about, 20 patients, and kind of along David's point, you wonder if, atrial flutter for 20 patients, does it kind of look the same all the time, such that a CNN could interpret it the same, or does, the 21st patient have kind of a, it looked close enough to this prototypical picture that a doctor would be able to recognize it, but far enough so that it wouldn't work on, via a neuron, so that a neural network might get confused.
Yeah, exactly. And this is what we find with the data sets that are available. Very quickly, once you start drilling down to a disease or an intervention, your N sizes start becoming quite small, and the sort of, the confidence then in the outcome start, really reducing. So here they've sort of done a gold standard test set, which I'll talk about in a moment, of only just a bit over 300 patients. And as you pointed out, as you drill down to a particular condition, and let's say that's a fairly unusual abnormality, then you're going to get down to pretty small numbers, and then perhaps your confidence around that's going to be questionable.
Awesome. Thank you.
No, it's Brent here. Just a quick note. I'm a physician, so I'll give you a few insights into the space. This is probably about as good as what we normally train our staff on, and what we do on a day-to-day basis. Although we talk about the clinician being gold standard, we're all exposed to variable traces, and so the training set is never going to be completely perfect, because if you only want two opinions, only put one clinician in a room. And the pictures that are here are fairly classical. It is a different way of recognizing arrhythmias. I mean, we're all trained with Ethiopian triangles and viewing the heart from different directions, whereas this is taking pictures and interpreting them as pictures. But the reality is that we train most clinicians on a picture basis at the end of it anyway. So looking at as little as we can see in the data sets, this looks fairly standard in terms of what we would train the clinician on. So if you take it from that perspective, if this is what we're training the clinicians on, then we train the CNN on that same data set, then it's probably okay.
Thanks, Brent. Brent's from IntelliHQ, so one of the intensivists that also love deep learning.
Okay. Another question that I had, just based on the headline, kind of the title of the paper, Cardiologist-Level Detection, is the comparison single lead versus 12 lead, or single lead versus single lead?
This is all single lead data. So yeah, at the end of the paper, they talked about further work starting to look at multiple leads, giving more resolution and being able to detect other conditions. But for a lot of the wearable devices that people are going to use at home, it's pretty much going to be down to single lead.
Okay. Once
you're in intensive care, then you'll have 15 leads. Brent is common in intensive care.
So that the standard full ECG is 12 lead. In an intensive care, you'd be likely to do more than 3 on a regular basis. You'll occasionally do a short 12 lead. The same goes for Holter recordings, which are longer term. Again, it's sometimes 1, sometimes 3 leads, but that's about it.
Okay.
So yeah, let me drill into the model, and then I'll come back also to then the testing, which is really the evaluation against cardiologists and how that was done. So pretty much they've used a fairly standard one-dimensional ResNet to train this algorithm. They've set up sort of filters of length 16. There wasn't any information in there about some of the striding or padding that they might have done around those signals. We've sort of made an assumption that they've then mapped that through to 30 different softmax outputs for the classes, each representing each second. We sort of discussed for a while, would you sort of slice it and look at 1 second at a time? We've been doing some other models with some research students starting to look at things like recurrent neural networks and things like that coming back. So there's other alternative approaches, but it looks like that in terms of training a model, this 1D ResNet's been pretty good. So I guess why a ResNet, they've got all the sort of standard batch normalization, relo, dropout. The residual network has these links at each block, which then sort of reduces the vanishing gradient problem by allowing sort of identity to flow back through the network if required. At each level, they're increasing, like every four blocks of every 4 residual blocks, they've increased the filter sizes, so going from 64, 128, 256 to 512 filters. They said they were using atom optimization. Not a lot of detail about hyperparameters and so on in that, and how they tuned the algorithm. They just said they used default parameters with like a reduced learning rate once the sort of loss leveled out and so on. So to me, it sort of looks like a fairly standard network that they've applied to this. So definitely something that we will aim to reproduce, but I'll talk about reproducibility a little bit later on. because without access to the data set, it's pretty hard to reproduce that. Any questions about the neural net and the model that's being used? Okay, so yeah, in similar areas.
I'll just jump in with a quick commercial. If that stuff is not familiar to you and you want to learn more about it or some of the details, this is all the stuff that this Fast AI course is covering right from the beginning. So once again, feel free to join us in taking that one.
Yeah. So, you know, much like a 2D neural net where different layers are learning different features, you would see the same thing in a 1D net. So I found this set of graphics from SoundNet where, say, the first level of convolution, you can see the filters that it's starting to learn are looking at detecting different sort of wave patterns that it would try to filter and identify in the signal, and then, you know, sort of build that up through different layers of convolution until coming to that fully connected network at the end.
You can start to see almost like different frequency components here. And Nick had a question, which was, has there been any thought given to combining neural nets with some of the traditional pre-processing like Fourier transforms or things like that?
That's a good question. We've been posing the same thing about just not so posing, but pondering even for our own data set creation. You know, how much do we use existing tools and then augment that with other labels and so on to actually help us start building up that data set to begin with. Yeah, and I'm not sure whether people have explored that in other areas of machine learning either, to use, you know, traditional methods to help build the labeling in the original data set, and then how do you then maybe use active learning to perhaps correct labels or find things where there's uncertainty and add that to the data set. But that's definitely an approach I think worth investigating. And also, I didn't mention in the lead up, but Google just put out a really interesting paper about using reinforcement learning for data augmentation. So in this approach, there's been no data augmentation. So unlike images where we might shift the image or flip it or stretch it and so on, there's been no sort of data augmentation on this data to try to help optimize the network. That'd be another interesting thing to look at as well. That paper from Google that came out, I'll try and dig up the reference, but they've now, you know, had, you know, best performance on ImageNet and so on as a result of discovering optimal data augmentation patterns.
Yeah, I think it would still be within the past couple posts within their research blog. It was relatively recent.
Yep. Okay, so we looked at the training data, and they split some of that into the validation data that they used to build up the model. In the testing, they've taken a slightly different approach. So they just didn't use a holdout set. They actually built a gold standard test set. To do that, the actual gold standard ground truth tests were they set up 3 sets of committees. Each committee had 3 cardiologists on the committee. They split the data, you know, the 300 odd patients or the 328 patients across those 3 groups. So that probably means that, you know, roughly 100 patients per group. And then the committee would discuss the individual record and agree on what the correct labeling for each 30-second slot, each second of the 30-second slot was, to have a consensus, right? In addition, so that's really what they're testing against. In addition to that, they also got cardiologists. So for every record, there were 6 cardiologists would provide their own label. And that was to actually evaluate how good are the cardiologists at doing this, right? So that way we can measure actually an individual cardiologist against the ground truth data set. And equally, we can measure the CNN against the ground truth data and see how they compare. And pretty much that's what's represented in the test results that they put forward. So there's two types of tests that they considered. One was sequential. So do we actually match up for each step in the 30-second labels, the correct label? So what's the overlap there of having the correct label in each slot? And then they also think about that as the set. So if we look at the set of labels that were generated for the 30-second trace as a whole, do we actually have overlap of the sets, right? And to me, it sounds like that, you know, probably from a diagnostic thing, I'd be first looking at the set. You know, have we, say, detected AFib in a trace in both of them? And when I first looked at this data, there were a couple here that performed worse. Let me do it like this. Trigger Mini, if I've got the pronunciation right, actually has lower accuracy than the sequential, which tells me that there might be just one label in the middle. So I got sinus rhythm right for the other 29, so I get quite a good score, but I missed out that one missing label. So, you know, normally I'd think that, you know, achieving the set of labels would be more achievable, but you can see there the variation in approach. Here they're measuring F1 score, which is the, I forget the technical definition, but it's like the, it's not the mean, but it's the sort of relationship between precision and recall, and it sort of punishes if those are quite different and distinct, as opposed to just the mean on its own. But what we don't see is like what the area under the curve is for each of these sort of areas, which might be more interesting data, and I'll come back to that in a second. They also provided some confusion matrices, which are quite helpful for understanding what it's doing. And yeah, so certain diseases like SVT, which off the top of my head is supraventricular tachycardia, saying that that actually correlates quite, you know, we saw there that it showed up to look quite close to an atrial flutter. But when you actually visually look at those, those are actually quite similar in their pattern. And so therefore it would be, you know, not unexpected that you get that sort of error floating across to another time. So there's a bit of discussion in the paper about those three particular labels and how they actually overlap with other disease categories. Okay. So back to this point about, you know, they didn't report the area under the curve, and I think this is, you know, it would have been quite interesting to know what actually for each of those diseases, what the false positive and false negative rates were. So they haven't indicated what threshold they're using. I'm just assuming it's at 0.5 as they're making as the decision criteria. But yeah, I think it's really interesting from a medical point of view to really understand false positive rates versus and false negative rates, because they have different sort of implications in terms of either people showing up too often for further diagnosis or not showing up for diagnosis. And I'll probably touch back on that in a second. But we discussed in our team and with Brent and so on about all these papers, and we've seen it with diabetic retinopathy, skin cancer and so on. They always talk about beating the clinician, right? And it's almost like putting up this, it's the computer versus the doctor. And, you know, this whole debate often then falls into things like, we're going to make radiologists redundant because AI is going to do all this work. But really our view is that for us, it's about augmented intelligence. It's about actually putting the two together. So my point about, actually I'll come back to the other point in a moment. And really, you know, when we start making this debate about the robot or the doctor, very quickly the public generally fall into this, well, I don't want to deal with a robot doctor. I want a human doctor. You know, I want that empathy. I want that relationship. But, you know, you go to other countries that don't have access to medical resources, they'd say, I'll quite happily take the robot doctor because I don't have access to any doctor at the moment. So you find this sort of relationship of feeling, but it doesn't really, this viewpoint doesn't really take into account this idea of augmented intelligence rather than saying it's one or the other. And certainly, you know, from a reliability and safety point of view, I think we need to up our game using AI to help, you know, diagnose these sort of gaps and errors because, you know, hospitals aren't a safe place to be. A good paper that really talks about how we combine the two, it goes back a little while, but it talked about putting the pathologist together with the AI, right? So in this study at the time, they had AI had a 7.5% error rate. Human pathologists had 3.5% error rate. But actually, we're not saying one or the other. We're saying the two together produce super performance. And the reason for that is around how we can actually dial back the sensitivity and specificity of our algorithm by changing its threshold. So what we often find with humans in the clinical area is that they have very few false positives. Once they see something, they can more or less confirm that's right. But if they're looking at, say, 3,000 cancer slides in pathology, and there might be 10 cancers in them, it's very easy to have a false negative and they miss things. So on the flip side, we should be able to dial back the threshold of our AI to have a much higher false positive rate because we know they're going to get filtered out by the pathologist. If that dialing back to higher levels of false positives means that we almost eliminate false negatives, we can see that that's how we get to really high levels of accuracy by combining those two methods. So where might a tool like this go? Well, you know, these sort of results and some of the questions asked about things like the sampling bias and the, you know, the efficacy of the testing and so on. That's a good start for looking at evidence. But if it was to progress towards a diagnostic tool, it would need to then go through some form of FDA regulation, possibly as a Class 2 device. There would have to be some measure of patient trial alongside with that. And if anyone wants to read about that, there's another heart rate monitor that we've been working with a bit called AliveCore that is FDA regulated, that is doing things like atrial fibrillation detection. But this is a fairly hot area at the moment. So the FDA recently came out that they're really looking at revising and updating this regulatory framework for AI, because I think AI has a lot of implications, particularly about this changing position of the data. There was quite a discussion about other data sets, and I think back to the comments made earlier, the numbers are really a reflection of we don't have enough data in the healthcare space really to build more powerful deep learning models yet. So the MIT data set's been used for a long time, where they've got 48 patients with 30 minutes of data. That's used by a lot of teams. LiveCore have recently put out 7,000 30-second ECGs. Apparently they've collected something like 20 million ECGs over the last 5 or so years. So those data sets are there, but what we're missing most of the times are the labeling of these. And I think this is what this paper has really gone about doing, is setting up these labels. So we definitely see that as well, as data is the new oil. And to give you, I think what's missing is, you know, for instance, in ICU, we'll start, now we're collecting all these ECGs as patient stays, but actually we want to now look in other databases that we've got to merge these databases, because in our electronic medical record systems, we'd have labels about diseases and about drugs and other things that now, if we can combine that data, it starts providing the labels that we can start building more powerful models. Google recently put out a really good paper and model, probably 2-3 months ago, about feeding into a attention-based sequential model. 250,000 patients from 2 hospitals out in California, and starting to predict a lot of accurate sort of outcomes and things like that. But yeah, you can see that one of the challenges we've had in the data sets is that how do we get to these larger numbers? MIT have an intensive care data set only with 60,000 patients that have lab results and observations every 15 minutes. And there's been lots of interesting publications about sepsis prediction. But as you drill down and start picking out a particular disease, very quickly you start getting down to, say, 4,000 patients or 1,000 patients, and your numbers reduce quite quickly from machine learning models. Also, the other work we've done is that they're just recording observations like high and low heart rate every 15 minutes. And we know as we've gone deeper, say getting down to the ECG, we will get more accurate predictions in terms of some of these outcomes like survivability and sepsis prediction and so on. So just starting to wrap up now, some of the limitations that we spotted. I think first of all, it's pretty hard for us to replicate this study, and there's been some criticism of AI about that because, yeah, we might, you know, we just submitted a paper and we had to put a GitHub library up with the code with Jupyter notebooks. But again, oftentimes the data set is not supplied because there's limitations or proprietary information associated with that. Very limited information about hyperparameters. This is really about a brute force supervised learning approach, you know, and it's really the key is about the labeling approach that they built and less about anything novel about the model. So, you know, really question marks around could we use active learning and data augmentation to more effectively do this with less labels in this space? And something we've started looking at is whether perhaps sequence models might be better at this. And there was an interesting debate, Jeremy Howard, about whether CNNs or RNNs are better at doing some of this sequence-to-sequence analysis. So for us, what we're looking at doing is trying to replicate that, but probably building our data set in a different way, looking at other deep learning models, other arrhythmias. But the other thing we want to look at is over longitudinal periods. What are some of these fatigue predictions or sepsis prediction and other things from the ECG data? And definitely matching up to EMR data to actually grab those labels out. The other thing we've been chatting a lot about is, you know, let's say we push this out and there's 24-hour monitoring of people. We've been working on one with ECG and a truck driving steering wheel to measure fatigue. As we push AI to the edge, we're not going to send all that data back. So do we start building up some sort of embedding or like an ECG to VEC type model that actually gives us a representation of what's going on that we can then feed that back in a sort of low fidelity mechanism back to, you know, further processing. So those are some of the interesting sort of research directions that might come from this kind of research. So pretty much I'm done there, Sam. I don't know if I've run over time or.
No, you are right on time. We've got a second or maybe a minute or so for a question or comment. Anyone have any questions? There's some, Andrew had some comments in the group chat about applicability of ROC Curve versus F-score. I don't know if you want to chime in on that, Andrew.
Yeah, you can still look at the ROC curve, but instead of using them, I haven't delved into research, so I can't, I'm not sure what exactly was being used. You said you weren't sure if they're using a 50% cutoff or not, but I was just putting out the comment that these heart conditions are inherently rare events, and being rare events, you have to be very careful about the true negatives diluting out your misclassification ratio. So instead of using a misclassification ratio as an optimization criteria, it's often good to use an F statistic instead, which puts all the weight on the true positives.
Okay, yeah. Yep.
This is a food for thought for anybody. I'm in a different sector. I'm not in the medical sector, but I know that with the work I've done in the past, that that was one strategy that had to be used.
Awesome, thank you. Any questions for Kelvin before we finish up?
Just a couple of quickies for me. I'm very interested in this area. So the whole purpose of all of this is to provide a diagnosis. So there's no requirement for the neural network essentially to be explicable. It doesn't need to explain why it came up with a diagnosis. You're just essentially using it as a black box. You're feeding in the data and you're getting a result out at the other side that then is being handed to a clinician to interpret. Is the explicability aspect of this important, or is just the mere fact that we can provide additional services to doctors to help them even a little bit a sufficient benefit that we don't have to worry about all these kind of more abstract problems that this kind of approach might have?
Yeah, explainability is a massive issue in this space. I think, yeah, even, you tell a doctor just believe the outcome because it's got like a AUC of 0.95 or something like that. That's not going to cut it. We just submitted a paper looking at sort of survivability prediction post cardiac arrest, and yeah, there's these other methods, but basically, a physician's got to understand also the biological rationale of what's going on, and make sure that that prediction makes sense. So we've started looking at things like Lyme, and I got that tip off one of Sam's podcasts from some time back looking at Lyme, and then there's other approaches like SHAP and so on. There's also specific approaches around sort of 2D images and sort of highlighting where in that image we're detecting that element, and you can see that also in, say, sequence attention models as well, highlighting what parts in the sequence are relevant. So yeah, I think any of these models would have to be accompanied with some explainability component. And I don't think the initial bit of that I wouldn't see as too difficult, using some of the existing approaches that are there to at least, at the moment, the 1 second labels are at least pinpointing the region where that is. Yeah, so as perhaps a screening tool, it's going to be quite powerful if you can apply it across a trace, give that to a clinician and say, here's the area that we're suspecting that something's wrong. That's at least a useful start. Then other things about why that's relevant, and maybe, looking at other clustering techniques to show them other traces where that condition was similar and so on. Those would be the kinds of techniques you'd want to apply.
Awesome. Well, Kelvin, thank you so much for a very, very interesting presentation. Everyone feel free to carry on with the chat and questions in the Slack channel. We'll get the slides posted there, as well as the Zoom chat transcript. Looking forward to next week's presentation by Nick. And once again, if you want to dive deeper into the deep learning stuff, the Fast AI study group is available. Thanks, everyone. Bye.